So we've been talking about infinite sets and saying that they are countable. So the concept of saying that something is accountable just literally means that there's a way to list every number in the list. You can kind of do it like I did over here in a table like that. In a different problem, I did a straight line and I kind of counted the numbers like that. So that means that the numbers are countable. So there's a way to represent all the numbers individually one by one. Now, not every set is countable. As a matter of fact, there are plenty of sets that are not countable. For example, the set of real numbers, it's automatically not countable. It's way bigger than the set of integers. So there's no connection between the two. So you can say that the set of real numbers is uncountable. In this case, I'm actually going to show you not only are the real numbers are uncountable, but the set of real numbers between 0 and 1 is uncountable. So even that tiny little piece on the whole number line from 0 to 1 has more real numbers than there are possibly even integers or integers in the world. That little section has more numbers, the real numbers, decimals, periods, whatever, than there are possibly integers. And the way we prove this is by doing sort of a proof by contradiction. This is all kind of going with the diagonalization process that Cantor introduces in year 1891. Okay, so this is fairly recent in the world of mathematics. This is a brand new kind of a theorem or a proof. And the way that his idea is to basically make a list of all the numbers between 0 and 1. So your list is going to start 0.102537. That's the first integer or the first decimal. And you go to the next one, and then you're going to put 1, 1, 2, 7, 3, 8, 9, whatever. And then you're going to go and list the third possible rational, or in this case, real number. So I don't know, maybe it's going to be 3, 7, 1, 5, 2, 6, 3, whatever. So keep doing that with as many real numbers as you can. Put them all in the list. So again, the idea that he introduces basically says, since we're going to do a proof by contradiction sort of, let's make a list of all the numbers between 0 and 1. And so your list has to start somewhere, and it's going to continue probably for a while before it ends. And so you're going to see all these numbers in the list. And if your list is complete, that means your set is countable. But if your list is incomplete, then that means your set is not countable, because you can always find new numbers to add into the list. You're not able to find all of them, basically. So that means you're uncountable. So the way that his proof works requires you looking at each one of these numbers one by one. And so he developed an idea saying this. If I go to the first number and I see a 1, I'm going to write down something like a 2. So if I see a 1, I'm going to write down 2. If I see anything else, I'm going to write down 1. Okay, so again, if you see 1, write 2. If you see the number 2, 3, 4, 5, 6, 7, whatever, 6, 7, 8, 9, or 0, write the number 1. Or whatever. You can write 0 if you want. Or you can write 10, whatever, it's up to you. You can write anything you want. He decided he's going to write, let's say, 1. Okay, so if you see any of these, you're going to write down the number 1 automatically. So on the first line, you look at the first number. On the second line, you look at the second number. It's a 1. So when I see a 1, I write down the number 2. Okay, then you go to the third line, you see the third number. It's a 1 again. Okay, so when I see a 1, I write down a 2. And now I go to the fourth number, fourth line. I see a 1. When I see a 1, what am I supposed to write? 2 again. Now on the fifth line, you're going to go to the fifth number, 1, 2, 3, 4, 5. It's a 2 this time. So when you have a 2, you write down 1. And then you go on to the next one. 1, 2, 3, 4, 5, 6. You're on the sixth line. The number there is 4. So what does that correspond to? It corresponds to a 1. And you could do that over and over and over again. Now, the special thing about this number that we're making, the new number that we created, is that, first of all, it's not going to end. It's going to keep going because there are additional numbers in the list. So it's going to continue on. And also, it is different than the first number in the first position. it is different than the second number in the second position. It is different than the third number in the third position. It is different than the fourth number in the fourth position. And you can see, you can keep it going all day long. It's different than every number out there in that whole list. So in other terms, it's not equal to the first number. This cannot be the same as the first number, or the second number, or the third number, or the fourth number, or so on and so forth forever. It cannot equal to any of the numbers in this list, because every time it's different than the first one, second one, so on in that position. So this is a brand new number that was not included in the list. And even if you think it's in the list somewhere, actually, you're going to have to follow the same recipe that we did here, and you're going to come up with a brand new integer, or sorry, brand new real number that is different. And so this is basically the idea. I'm able to create a brand new number that wasn't there already, which means that the set of these guys over here is uncountable. So there's a full proof in your book that kind of describes this a little bit more elegantly. I would recommend you read it and just kind of like know it. You're not responsible to make the proof yourself. You just kind of need to know and understand what the proof does and how it works. Now, there's a couple last items here on this list, just things good to know. A subset of a countable set is automatically countable. So if I know that the set of integers is countable, then if I take a subset of it, like the positive integers, then it's going to be countable. If I took the set of multiples of 3, it's automatically countable. If I took the set of even integers, it's automatically countable, and so on, because the original set that we started with is countable. Also, any set with an uncountable subset is uncountable. So since the set from 0 to 1, the real number from 0 to 1 is automatically uncountable because of this proof, then that tells me that the real numbers are automatically uncountable. Remember, the real numbers is bigger than the 0, 1. If the 0, 1 is already something you cannot count, then definitely you cannot count the real numbers themselves, because 0, 1 is part of it and you can even get the job done. So how can you do it with the set of real numbers all together? So that's basically what's going on with the last two, theorem and corollary.